If the sky's blue because the air is blue, then tonight the moon should look like it's shining through a giant blue glass bottle, so why doesn't it? You've heard the standard answer 1,000 times. Rayleigh scattering. Sometimes it's phrased as blue light scatters more, and the story ends right there, as if a label counts as an explanation. But that phrase is like saying a song exists because of music theory. It's not wrong, it's just, it doesn't tell you what's actually happening. So let's do this the way a stubborn person would do it. We're going to act like we don't know the magic words. We'll take what you can observe with your own eyes, and we'll ask what would have to be true about light and air for that observation to happen. And if we do it carefully, by the end, the sky won't feel like a painted ceiling anymore. It'll feel like a physical process that you can almost hear humming. Start with the simplest observation. In the daytime, the sky away from the sun is bright and blue. At night, with the sun gone, that same air is basically invisible. That alone tells you the air is not intrinsically blue in the way a blue shirt is blue. A blue shirt looks blue because it absorbs a lot of the other colors and reflects more of the blue back to you. If the atmosphere worked like a giant blue filter, it would keep filtering all the time. It would tint moonlight blue, it would tint starlight blue, and yet the night sky is not a luminous blue dome. The air disappears when the sunlight disappears. So the blueness must be something the air does to sunlight, not something the air is. Now think like a detective. The sun is basically white to your eyes, meaning it contains a broad mix of wavelengths, reds, greens, blues, and all the colors in between. Yet when that white sunlight floods the atmosphere, some of it ends up coming at you from directions that aren't the S. That's the crucial point. If you look 90 degrees away from the sun, you still see light. Where did it come from? It's as if the air itself becomes a light source, not because it glows on its own, but because it is taking light that was traveling one way and sending some of it out in other directions. That sending out in other directions is what we mean by scattering, but we're not going to let the word do the work. We're going to ask, what does it mean physically in terms of stuff in the air and forces and motion? Here's the first mechanical picture to hold in your mind. Light is an electromagnetic wave. That's not poetry. It means that at every point in space, there is an electric field and a magnetic field that wiggle in time. And an electric field exerts forces on electric charges. Even if the air is neutral overall, it's made of atoms and molecules, and those contain charged particles, electrons and nuclei. So when sunlight passes through air, it brings with it an oscillating electric field that pushes and pulls on the electrons in those molecules. It's like a tiny, rapidly alternating shove. First this way, then that way, billions of times per second. Now, what happens when you shake charges? A charge that accelerates radiates electromagnetic waves. That's not a special property of the sky. It's a general fact about electromagnetism. Accelerated charges emit radiation. So the picture is, sunlight's electric field drives the electrons in molecules to jiggle. Those jiggling electrons are accelerating back and forth. Accelerating charges re-radiate light, and that re-radiated light goes out in many directions. That's the first big aha mechanism. The sky is not colored paint. It is the byproduct of trillions of tiny driven oscillators, molecules whose electrons are being shaken by the sun's electromagnetic field and then broadcasting light sideways. If you take only one molecule, this effect is absurdly tiny. The molecule is not a mirror. It's a minuscule object compared with the wavelength of visible light. But the atmosphere contains an enormous number of molecules, and the scattered light from all of them adds up to a visible glow. So far, that explains why the sky is bright away from the sun. But it doesn't explain why it's blue. If the sun's light contains all colors, why doesn't the atmosphere scatter all of them equally, making the sky white? Here is where the usual explanation tries to do the whole job in one sentence. Blue scatters more. We'll make that sentence earn its paycheck. Ask yourself, if you shake an object at different speeds, will it respond the same way? If you slowly push and pull on something, you get one kind of motion. If you vibrate it very fast, you can get a very different response. Now translate fast and slow into light, Different colors correspond to different frequencies. Red light has a longer wavelength and a lower frequency. Blue light has a shorter wavelength and a higher frequency. Violet is even higher. So we're asking, when sunlight's electric field shakes the electrons in a molecule, does the molecule re-radiate different wavelengths with different strength? Yes. Very stiff. Wrongly, yes. But to see why, we need one more step in the mechanism. Not a wall of math, just a clear model. Imagine the electrons in a molecule are not free beads sliding around. They are bound to the molecule by electrical attraction. If you pull them away from the nucleus, the molecule pulls them back. So the electron behaves a bit like a mass on a spring. Light's electric field is the driving force. The binding acts like the spring pulling it back. Now, in a driven oscillator, the amount of oscillation you get depends on the frequency of the driving force compared to the natural frequencies of the system. Molecules have natural resonant frequencies, typically in the ultraviolet for electronic transitions. Visible light is below those resonances, but not infinitely far below. In that regime, well below resonance, the induced motion behaves in a way that leads to a very steep dependence of scattered intensity on wavelength. The clean result for very small particles is that the scattered intensity goes approximately like 1 over the wavelength to the 4th power. 1 over wavelength to the 4th. That is a brutal dependence. What does it mean in plain language? It means that if you go from red light to blue light, the scattering doesn't just increase a little. It increases by a factor that's big enough to matter to your eyes. Let's do a sanity check without getting lost in numbers. Blue light has a wavelength roughly around 450 nanometers. Red might be around 650 nanometers. If scattering scales like 1:4, then the ratio of scattering for blue versus red is about 650, 454. That's more than a factor of 4. And that's the kind of difference that turns white light into a blue-tinted glow when you're looking at the scattered light. So now we can say the slogan with meaning behind it. Shorter wavelengths get scattered much more strongly by molecules because the tiny induced dipoles radiate in a way that depends steeply on wavelength. But here's where the title's promise really lives, because if you stop there, you've explained something. And yet, you haven't explained what most people really mean when they ask why. Most people are not satisfied by its scales like 1L4. They want to understand what that scaling is telling you about the physical process. They want to feel why shorter wavelengths should be favored. So let's make it more physical. Think of the atmosphere as a gigantic crowd of tiny doorbells. Sunlight is the finger pressing the doorbell button, but it's a finger that's pressing and releasing incredibly fast. Every time the electric field swings one way, it pushes electrons one way. Then it swings back and pulls them back. That back and forth motion is an acceleration. And accelerating charges emit radiation. Now imagine pressing that doorbell slowly. Press, release. Press, release. The bell rings, but it's not very energetic. Now imagine forcing it to vibrate much faster. In a certain range, a faster driving can lead to larger accelerations and a more vigorous re-radiation. The exact details depend on the system, but the big idea is that the ease with which the electrons can slosh around in response to the field depends on how quickly you try to drive them relative to their binding. The key is that for small particles, the induced dipole moment and the way it radiates led to that sharp wavelength dependence. Shorter wavelengths are like more rapid shoves, and the re-radiated power you get sideways ends up being very sensitive to that. If you want another concrete picture, think about waves on a crowd. A slow swell passes through, and individuals don't have to move much. A fast ripple forces more rapid motion. Again, it's not a perfect analogy. Electrons aren't stadium fans, but it helps you feel why a system can respond very differently to different frequencies. Okay, at this point, we have a satisfying chain. White sunlight enters atmosphere. The electric field drives electrons in molecules. Driven electrons accelerate. Accelerating charges radiate. The re-radiated light is much stronger for shorter wavelengths. The sideways light you see from the sky is enriched in blue. That sounds like done, except we're not done, because there's a trap hiding in that explanation that your brain will notice if it's paying attention. If shorter wavelengths scatter more, then violet light should scatter even more than blue. So why isn't the sky violet? Why isn't it purple? This is one of those questions that gets brushed aside in a lot of explanations, but it's not a minor detail, it's a clue. It tells you that you're missing at least one piece of the story. Let's take the question seriously. First, your eyes are not measuring instruments that respond equally to all wavelengths. Human vision is much less sensitive in the violet part of the spectrum than in the blue-green region. So even if there is a lot of violet scattered, you may not perceive it as strongly. Second, the sunlight itself is not perfectly flat across wavelengths. The sun's spectrum has a shape. It emits less in the violet than it does in the green-yellow region, and the atmosphere can also absorb some of the shorter wavelengths at high altitude, which further reduces what reaches your eyes. So the sky's color is not determined by scattering alone. It's determined by scattering multiplied by what's available to scatter, multiplied by how you perceive it. This is a crucial kind of intellectual honesty. When you say the sky is blue, you are describing a human sensation, not an objective label attached to photons. The photons have wavelengths. Your brain has a color experience. So the why not violet problem is solved by a combination of physics and biology. The physics makes short wavelengths preferentially scattered. The biology makes blue dominate your perception. Now you might say, fine, so the sky has some violet in it, but we don't see it much, and blue wins. That's good. But there's another layer. If you've ever been at high altitude on a very clear day, the sky can look a deeper, darker blue, almost like the blue is saturated. And near the horizon, the sky looks paler, sometimes almost white. And near the sun, it can look washed out. So what's going on there? If Rayleigh scattering is the whole story, why isn't the sky the same shade everywhere? This is where geometry and the amount of atmosphere you look through matters. When you look straight up, you're looking through less air than when you look toward the horizon, where your line of sight passes through a much longer path in the atmosphere. A longer path means more scattering events. But here's the subtle point. More scattering doesn't always mean more blue. With a small amount of scattering, the scattered light you see is strongly biased toward blue because the shorter wavelengths are preferentially scattered once. But if the path is very long, light can be scattered multiple times. And multiple scattering tends to mix things and wash out color contrasts. It can also increase the amount of longer wavelength light that ends up coming from that direction. And then there's another regime. Not all scatterers in the atmosphere are tiny molecules. There are also larger particles, dust, aerosols, pollution droplets, water droplets in haze. Those are often comparable to or larger than visible wavelengths. When the scatterers are large compared to the wavelength, the scattering behavior changes. It becomes less strongly dependent on wavelength. That's why clouds are white. A cloud is made of water droplets big enough that they scatter all visible wavelengths more nearly equally. The light bounces around many times inside the cloud and comes out as a fairly even mix. White. So you can think of the atmosphere as having two modes that compete in your visual experience. Mode 1. Molecule-sized scatterers, strong wavelength preference, blue sky. Mode 2, larger particles and multiple scattering, weak wavelength preference, whitening, hazing, and sometimes reddening effects by removing blue from the direct beam. Now let's connect this to sunsets, because sunsets are the emotional payoff most people love, and they're also a great consistency check for our mechanism. At sunset, the sunlight travels through a much longer path in the atmosphere before it reaches your eyes. Along that long path, the shorter wavelengths, blue and violet, get scattered out of the direct beam. Where do they go? They don't vanish. They get sent sideways into the sky in other directions. That's one reason the sky around can glow with color, while the sun itself looks redder. By the time the light reaches you directly from the sun at sunset, it's missing a lot of its blue. What's left is weighted toward red and orange. So the sun looks warmer, and the sky away from it can have complex gradients, depending on particle sizes and multiple scattering. So the blue sky and the red sunset are not separate tricks. They are the same mechanism seen from different angles and path lengths. Now here's a point that many explanations skate past. When you say blue light scatters more, you might picture photons of different colors physically bouncing off molecules like billiard balls and changing direction. That picture can lead you astray. What actually happens in a wave description is that the incident electromagnetic wave drives oscillations in the charges, and those oscillations radiate. The scattered light is not a single photon ricocheting like a ping-pong ball. It's a re-radiated wave produced by the molecule's induced dipole. In a quantum picture, you can talk about photons being elastically scattered, meaning they keep their energy but change direction. But even then, thinking in terms of bouncing can hide the real mechanism. which is that the molecule acts like a tiny antenna. That antenna idea is powerful. It lets you unify a lot of things. For example, why does the sky have polarization patterns? Because radiation from an oscillating dipole is not emitted equally in all directions with all polarizations. The scattered light has preferred polarization depending on the scattering geometry. That's why polarized sunglasses can sometimes deepen the sky's color at certain angles. They're filtering one polarization component, enhancing contrast. You don't need to memorize that as trivia. It's a test of the mechanism. If you really believe the tiny antenna model, polarization effects make sense as a natural consequence. Now let's step back and ask, what does the title really promise? It says nobody explains why the sky is blue like this, meaning you're not just getting a fact, you're getting a way of seeing. So let's build a mental movie you can carry around. Imagine you're floating above Earth looking at the atmosphere as a thin shell. Sunlight enters this shell. As it passes through, every molecule becomes a microscopic broadcaster. Most of the sunlight continues straight through, but a tiny fraction is re-radiated in all directions, and that fraction is heavily biased toward shorter wavelengths. So the sky, from any given direction you look, is light that originally came from the sun but has been sideways broadcast to you by the atmosphere. If you look straight at the sun, you mostly see the direct beam, brighter and increasingly redder when the path length is long. If you look away from the sun, you mostly see the scattered broadcast, bluer because the broadcast is short wavelength heavy, and if there are large particles or droplets, they act like different broadcasters that don't have such a strong wavelength preference, and they mix the colors toward white. That's the unified picture. Now, if we're really doing this in a Feynman spirit, we should ask, are we done? Do we now know why the sky is blue? It depends on what you mean by why. We can answer how with extraordinary precision. We can describe the chain of cause and effect. We can even calculate the scattering cross-section from electromagnetism and statistical properties of the atmosphere. That's a how answer. But sometimes when people ask why, they mean something deeper. Why does nature choose this particular law where accelerated charges radiate? Why does the scattering scale the way it does? Why do atoms have these particular polarizabilities? At some point, why becomes because that's how electromagnetism works. And then you can ask, why does electromagnetism work that way? And you end up at the base of physics where the answers become the laws themselves. That's not a failure. That's a mose. P of what science is. Science doesn't hand you ultimate metaphysical reasons. It hands you mechanisms, relationships, and predictions. And the mechanism here is gorgeous because it takes something you see every day, the color of the sky, and ties it directly to the behavior of electric charges under oscillating fields. Now, before we synthesize everything, I want to do one more thing, give you a way to feel, scattering without needing the entire sky. If you want to fake a sky in a glass, you can. But you have to be honest about what you're imitating. Take a clear glass of water, shine a bright flashlight through it in a dark room. If the water is perfectly clean, the beam is hard to see from the side. That's because there's not much scattering. Now add a tiny amount of something that creates very small particles in suspension, like a drop of milk stirred into the water, or a bit of sugar solution that creates fine scattering centers. Don't overdo it. With the right concentration, you'll see the beam from the side, and it can look bluish, while the transmitted light can look slightly warmer. That's not literally Rayleigh scattering by molecules anymore. Milk droplets can be larger, and the regime can shift. But conceptually, you're recreating the key idea, a medium that takes light traveling one way and redirects some of it into your eye with wavelength-dependent effects. And if you add too much milk, something interesting happens. The beam gets bright and whitish. The color contrast disappears. That's your intuition for what haze and clouds do. Multiple scattering and larger particles wash out the wavelength bias. So even with a glass, you can watch the transition from bluish scattered light to white scattered light as particle size and concentration change. That's not a cute party trick. It's a miniature laboratory for the same physics. Okay. Now let's deliver the promised like-this explanation in one clean synthesis and make it feel inevitable. The sky is blue because sunlight is an electromagnetic wave, and electromagnetic waves push on charged particles. The air is full of molecules whose electrons can be displaced slightly by the sun's electric field. That displacement makes each molecule a tiny oscillating electric dipole. An oscillating dipole radiates electromagnetic waves outward, light, into directions other than the original direction of the sun's beam. That re-radiated light is much stronger at shorter wavelengths, roughly scaling like 1 over the wavelength to the 4th power for molecules much smaller than the wavelength. So the sideways broadcast that fills the sky is enriched in short wavelengths. But the sky isn't violet because the sunlight spectrum has less power in violet than in the middle of the visible range, and because your eyes are less sensitive to violet. So the scattered short wavelength light is perceived predominantly as blue. And the sky changes with direction and weather because the amount of atmosphere you look through changes, and because larger particles, dust, aerosols, water droplets, scatter light differently, tending towards. Each colors toward white and producing haze and cloud brightness through multiple scattering. So the sky isn't blue stuff. It's white sunlight being continuously rebroadcast sideways by trillions of tiny driven charges, filtered by wavelength and finished off by your eyes. And now here's the part I really want you to keep. Once you see that, you can't unsee it. You look up and realize you're watching electromagnetism in action at planetary scale. You're watching the interaction between radiation and matter, the same physics that makes a blue smoke plume, a white cloud, a red sunset, and even the blue tint in distant mountains. The next time you're outside, try this. Look straight up on a clear day, then slowly sweep your gaze toward the horizon. Watch the blue pale out. Ask yourself, am I seeing more scattering or different scattering? Then look at a cloud and notice how it's not blue at all. It's white because the scatterers are bigger and the light is bouncing around until it forgets its original color bias. Once you adopt that lens, every color in nature starts to look like a physics question wearing a disguise. And maybe that's the best ending for a why question, not a final period, a new kind of curiosity.